Ah, okay, so let's go ahead and get started for today. Continuing uh, with our chapter on kinematics, where we've been talking about deformations or just describing deformations. Any questions on any of the material that we've covered so far, or from the homework? You all started homework 4? Go ahead, Spencer.
This would be a hard question to ask a better one-on-one. But like, what is like the Z? Like it's like phi is Z. I posted on the forum.
Oh, you did? Oh, okay. I haven't checked this morning.
But it's like phi of Z, and then it's like something Z minus constant times Z2 or something. Like, what is the actual Z that you would like?
Okay, so let's take an example. I guess what you're saying is, how do I understand the deformation map, right?
Yeah, essentially, yeah.
Yeah. So if it's a simple map like a translation map, then maybe I should take an example. So let's say I have a black undeformed body, um, a unit cube initially. That's my initial undeformed body, and I'm saying that phi. So all these axes are z1, z2, z3, and just like we said, to keep in the same coordinate system for the deformed and the undeformed, I'll also measure x1, x2, and x3 along the same directions. So if I look at, let's say, the uniform expansion map, the uniform expansion map is phi, or x is equal to phi of z, which we said was alpha times z. Now, pick any point in this domain. So this point, for example, is 1, 0, 1. Agree? This corner up here is 1, 1, 1. And so in that way, you can pick any point anywhere within this body. And actually, even outside the body, the map doesn't really apply to points outside the body. But we are just saying that any point in there, this is a point that gives you the coordinates of some point z. So if you pick a point z that you know these coordinates, then the deformed coordinates would just be alpha times this. So for example, let me call this point A. Let me call this point B. Phi of A would be represented by alpha 0 alpha, and phi of B would be represented by alpha alpha alpha. In this way, you can pick any point you want. Give me the coordinates of the points in the undeformed configuration. The map gives you the corresponding coordinates in the deformed configuration. Is that what you were asking?
Yeah, it's better. It helps you visualize it.
Okay, sure. Any other questions? Okay, yeah, go ahead, Kevin.
For the last part in problem 3, or can you go over like how to define like S for when you're trying to like find like the length?
Okay, I'll actually do that in the review session today, maybe at 3:30. That work? Okay, all right. So let's go through and very quickly revisit where we were. We talked about this deformation map like we just did. Based on the deformation map, we came up with something called the deformation gradient, which was nothing but the gradient of a vector field, right? Deformation map is a vector field. It associates with each point the position of the position vector in the deformed coordinates. So deformation map gives you a vector field, and gradient of that vector field should be a tensor field, which we studied back in chapter 1. And indeed, that is what this f is. F is the deformation gradient, and a very useful way of interpreting what f is this logic. Excuse me. That if you have an undeformed body, this black body, you go to any point in that undeformed body, like the couple of points that we just chose, the neighborhood of that small point, a small neighborhood of that point would be, you can consider infinitely many possible arbitrary unit vectors in that neighborhood, or actually infinitesimally small vectors dz. Those would be tangent vectors to infinitely many curves in the neighborhood of that point. That small black sphere kind of represents all the possible tangent vectors in the neighborhood of that point. After deformation, this goes to this blue configuration. That black sphere in the neighborhood of that point becomes this blue ellipsoid. So the interpretation of f is that it takes undeformed tangent vectors to deformed tangent vectors. That's all that this f does, which pretty much captures the state of deformation at a point in a body in all possible directions. That's what f does. That's what a tensor field is supposed to do. So using that, we came up with some definitions of stretch and strain. We said that stretch in the 1D direction in a one-dimensional definition of stretch was final length divided by original length. That was lambda, the stretch, right? We extended that to arbitrary directions. So if I have some curve in three-dimensional space, something like this, after deformation it might become something like that. We correlated the tangent vector to the undeformed curve with the tangent vector to the deformed curve just by using n. That n vector is a tangent vector in the undeformed configuration. That allowed us to say that the square of the stretch is equal to n dot product with c acting on n, where c is f transpose f. That was so we created this new deformation tensor using f, and that allowed us to calculate the square of the stretch in any given direction. Based on that, we came up with this definition of strain, the Lagrangian strain, which we said that if the only action of f is to rotate the tangent vectors, then there is no straining, and which is what allowed us to define this measure of strain, the Lagrangian strain. We also looked at a left-hand side strain, or a left Cauchy-Green deformation tensor and strains. And then we were doing some of these examples last time. So we looked at translation. We found that deformation gradient is identity. The Cauchy-Green deformation tensor is identity. It's an identity field, by the way. At every point in the undeformed coordinates is the same tensor, identity tensor. And I think I showed you an example of a tensor field with one of the MATLAB codes that is now posted. So if I can possibly run that again. Let's see if it connects. There we go. So last time I showed you this undeformed configuration with actually infinite many points, but here I'm plotting those points at a grid. Go to the neighborhood of any point, a black sphere goes to a blue ellipsoid, which pretty much captures the state of deformation of the entire body at each point in all directions. So this is what a F tensor field looks like. You associate a tensor, an ellipsoid, with each and every point in the body. So back to this. We looked at the uniform expansion, and we were looking at some of these examples from the book. So the first one was a simple shear example where you take the top edge and shift it by some amount beta. And we found the F, C, and E tensors for that. Another one is if you have uneven or uneven stretching in the two directions. In this case, would the F tensor be uniform? In the first case, in the simple shear case, F tensor came out to be 1, 1, 1 beta, which clearly does not depend upon Z, right? So it is the same F tensor everywhere. But here, if you look at the F tensor, the deformation map is given to you, and the way to understand this deformation map again is Z1, Z2, Z3 in the E1, E2, E3 directions remain the same. And what we are doing is we are adding beta times Z1, Z2 in the even component, which is what results in the horizontal displacement of each and every point. As we go more in the Z1 direction, we get more and more displacement to the right. As we go up in the Z2 direction, we get more and more displacement to the right. That's what this term, beta Z1, Z2, does in the even direction. The same term we have in the E2 direction as well. So as we go more and more in the Z1 direction, we get more and more vertical displacement. And as we go more and more in the Z2 direction, we get more and more vertical displacement, which is what causes this type of a deformed shape. So clearly, f in this case is a function of z. There is z1 and z2 in the expression for f, which means that the deformation tensor would be varying from point to point. It would not be just the same ellipsoid everywhere. Let me ask you this. Is there any point in the domain at which the deformation tensor is identity? Meaning black sphere going to a blue sphere of the same size? Origin. At the origin, there is no deformation. If you go anywhere away from the origin, there is some small deformation. As you go out to this point out here, you have the maximum deformation. The ellipsoid would be uh, tilted in this direction. And with the code that I've given you, you can actually plot some of these tensor fields. Another very interesting example is that of pure bending. What is pure bending, by the way? Only moment. So if you draw the shear force diagram, it's zero. And the bending moment diagram is a constant bending moment diagram. That's pure bending. And as I mentioned, if you apply some moment to a cantilever beam, then one of the solutions under beam theory is that it would curve up in a circular arc. If you apply enough moment, it will actually go up and curl upon itself in a perfect circle, which is very similar to one of your homework problems. So with some of you have tried to interpret this map, but I think what you should do is to make sure that this map essentially captures each and every point in the undeformed configuration, and you can verify that each of these points goes to the corresponding point in this curled up configuration. So given this map, we can easily find f, which is derivative of the x1 term with respect to z1, z2, z3, derivative of the x2 term. This is all, so maybe I'll write that here. This all is x1. All of this is x2. And clearly z3 is x3. If you take derivative of x1 with z1, you get the first term. Derivative of x1 with z2, this term. And with x3, it doesn't depend upon x3, and so on. We did those types of derivatives. So we can calculate f, which again is a tensor field that depends upon z. So again, it is not constant everywhere, right? And if you calculate f transpose f, that is the C tensor, f transpose f. So all you do is take transpose of this, multiply, and matrix multiplication with the components of f. You get this C tensor, which doesn't have those sine and cosine terms. What you can clearly see here is that C tensor is almost an identity with only one term that is capturing the effects of bending. What is this? Is there a good way to interpret this term? 1 minus z2 square with respect to this undeformed configuration?
Z2 is 0, then there is no.
Right, so if z2 is 0, this becomes identity, which means that the center line out here, that's where z2 is 0. There is no deformation. Okay, it just, that line goes all the way around maintaining its length. If you go positive z2, you would get numbers lesser than 1 here, right? Positive z2 numbers lesser than 1, which means compression. All the fibers above for positive z2 values would get compressed. All the fibers with negative z2 values would get extended, which is what bending does, right? compression fibers gets shortened and tension get elongated. All right, so these are kind of ways in which you would interpret deformation, deformation maps and deformation gradients, and the deformation tensor C that we've talked about, and the same sort of interpretation also extends to strain tensor E, which is just C minus identity. So let's see that if we can come up with some more physical meaning of these components of C and E. We saw for a different number of maps, we got this C. What do these components mean? We got another C out here. What do these components in general mean? So that's what we're going to try to understand. Okay. Now, of course, any tensor will have components along the diagonal and the off-diagonal components. So for the diagonal components, let's see if there is a good way to understand the diagonal components first. And to do that, what we'll do is try to take advantage of the relationship that we came up with for the square of stretch in some direction n. Okay, you remember we just on the previous page we said if you have some body, some undeformed to deformed body in the neighborhood of a point, consider some curve, and the tangent along that curve is, let's say, given by n, then the stretch in that direction is going to be given by n dot with Cn, where n is a unit vector. Okay, the square of the stretch is that. So that's we'll use that to interpret some of the components of C. Can you tell me what I would get if I were to do Cij? If I have, let's say, if I have some tensor C, which is given by components C11, C12, C13, C21, C22, C23, C31, C32, C33. So if I want to pick out the component, let's say 1, 2 from the components of C, can you come up with an expression in terms of the C tensor that would allow me to pick out component C12? That's correct. So C, the component here, if you were to write the only that as a tensor components, so everything else is 0. This is indeed C12, E1, dyad, E2. But how do I write C12 on the left with something C? If I act this on E2, I'll get some vector, right? And if I take the dot of that with E1, do I get C12? Let's check. If I act this tensor on E2, that would be 0, 1, 0, that's E2, right? If I do that, the result of that would be basically picking out the middle column, correct? So that would pick out the middle column, and it would give me C12, C22, C32. And if I then take a dot product of that with E1, which is 1, 0, 0, then I get C12. So in general, Cij would be equal to Ei dyad or dot product with C acting on Ej. Right? You pick whatever value of I and j you want between 1 and 3. You can pick out any of those 9 components using Ei dot with C acting on Ej. So I'll write that on the out here. Cij is equal to Ei dot with C acting on Ej, and actually I should not use E but G because C will act on the deformed tangent vectors. black. G, I, G, J. So for simplicity, I've assumed them to be in the same direction, but C does not act on the undeformed, uh, on the deformed tangent vectors E1, E2, E3. C acts on the undeformed tangent vectors G1, G2, G3. Okay, which picks out the ij component of C, and similarly the strain also is basically Gi dot E Gj. And now this gives me a good way to interpret the components of the C and E tensors. If I pick, let's say 1, 1, for example, then that would be G1 dot with C acting on G1, which is nothing but G1 dot with C acting on G1, the square of the stretch in the G1 direction. Okay, so at any point, C11 will represent the square of the stretch in the G1 direction. C22 would represent the square of the stretch in the G2, and similarly in the G3 directions. So these are called normal stretches. You remember in strains we used to have normal strains and shear strains. So this is what a normal strain really is. Question? Okay. Um, so these are normal stretches, and even E11, E22, E33, these are the normal strains, which are very, if you remember, epsilon XX, epsilon YY is what we used to call them, probably back in your sophomore or junior year. Okay. So this is for the diagonal components of C and E. There is a very nice interpretation that these are the normal square of the normal stretches in each directions. Let's take a look at what might be the off diagonal components. And as you expect, yes, they are related to the shearing of the body. So let's see how we can interpret that. Again, we'll take a look at this body which is getting deformed to this black body, getting deformed to the blue body, and the neighborhood of a point going from black sphere of arbitrary tangent vectors to blue ellipsoid of tangent vectors. And what we'll do now is consider two independent tangent vectors, n1 and n2. The initial angle could be anything. It doesn't have to be 90 degrees. All I'm trying to find out is if I have two tangent vectors in the undeformed configuration, what is the change in angle that they undergo after deformation? Okay. If it is pure rigid body rotation, the change in angle would be 0, correct? If it is a pure rigid body rotation, then this black sphere would go to a blue sphere where all the relative angles are still maintained. But in general, the angle between two vectors is going to change. So I have these two vectors, n1, n2, not necessarily related to anything to do with eigenvectors, but I'm calling them n1, n2. They go to fn1 and fn2, which again, that's the action of f. Now, if I try to figure out what is the new angle theta between fn1 and fn2, that can be simply obtained by dot product. So the dot product of fn1 as this vector with this vector gives me the definition basically of the dot product, cosine of the angle between them. You take cosine this to the other side, we get fn1 dot fn1 and the magnitudes of those vectors in the denominator. So we should be able to see, first of all, that fn1 is related to the stretch in the n1 direction. You remember we did that? If this is n1, it gets stretched to fn1, and just by the definition of f, we said that the stretch in the n1 direction would be the length of the deformed final vector. The length of the deformed final vector is the magnitude of fn1 divided by the length of the undeformed vector. Okay. Now, without loss of generality, I can choose length of the undeformed vector to be 1. That's a unit vector. I can say that I can pick a curve and a parameter s that matches the length of the curve. In that case, the tangent vector will be magnitude 1. Similarly, for lambda 2, I have fn2, that's the length of the final deformed tangent vector divided by the magnitude of n2. Again, I'll pick n2 equal to 1. So fn1 can be replaced with lambda 1, fn2 can be replaced with lambda 2. That's what I've done down here. On top, we still have fn1 dot with fn2. Again, using the definition of the transpose of f, I can write that as f transpose f, and that's just C. Okay. Um, all right. So that just gives me the cosine of the angle between the final deformed tangents. If I now measure the change in angle, which is if the initial angle was theta naught, the final angle is theta. If I measure theta naught initial minus final angle, that can be obtained using this expression. And in particular, if n1 is perpendicular to n2, if n1 is perpendicular to n2, then initial angle would be pi over 2, and we can pick any two directions. For example, if I pick g1 and g2, then I would get the change in angle between g1 and g2 in the original configuration minus what they would be in the deformed configuration. I can do this for any two tangent vectors. But in particular, if we choose n1 and n2 to be one of the basis vectors, then we get the shear, and hopefully you remember that shear is really the change in angle between the coordinate directions. So what we get is pi over 2 as it is, substituting the value of theta that we just computed out here, g cosine inverse gi, and there should be a dot here, by the way. There should be a dot. C acting on Gj, that gives me a vector, and then dot with another vector, that gives me a scalar, divided by the magnitudes of the stretches in those two directions. That's the final angle, minus the initial angle, that's the shear. So can you tell me what this is, C, Gj, Gi? On the previous page, we just said that that is Cij, correct? So when I is equal to j, what happens? If I is equal to j, what do we get? Let's say C11, for example, right? C11 in the numerator and the denominator, square root C11, square root C11, that becomes C11. And by the way, there is no sum on I. This is an exception to the summation convention. So this becomes 1. Cosine inverse of 1 is? Cosine inverse of 1, 0, right? So pi over 2 minus 0 gives me pi over 2. So the change, so the shear would be saying that there is basically, actually initial angle would not be 0, it would not be pi over 2. Initial angle would also be 0, right? So you obviously cannot have shear between the same vectors. But if we choose two different values for I and j, let's say 1 and 2, so this would become C12 divided by stretch in this one direction, stretch in the two direction, and then we get that interpretation that this value, the change in angle, is indeed the shear. And let's check that for this simple shear example. For the simple shear example, we calculated F to be that tensor. We calculated C to be this tensor with beta on the off diagonals. Now, what we'll do is try to figure out what this angle would be between E1 and E2. So to do that, let's figure out theta between G1, G2. So this would be pi over 2 minus cosine inverse. All I'm doing is plugging in this angle and trying to see whether that would be the shear. So cosine inverse of C12. C12 is this guy. Sorry, not F, but this one. C12 beta divided by 1 over beta square, which is the stretch in the two direction. Stretch in the one direction is just 1, so square root of 1, no need to write that. What we have is this. If you simplify this, you can show that let's do that actually. So if beta is small, right? If this length, if this amount by which this stretches, that beta, if that beta is small, then the denominator 1 plus beta square can be treated as 1, right? And what we have then here would be pi minus 2 beta. You can verify that. You can that cosine inverse of beta can be approximated as pi minus 2 beta, and that cancels off, and what I'm left with is that that entire thing is beta. So this angle turns out to be close to beta because this is a unit square, and that is indeed the shearing angle, a measure of shear in this body. Okay, question? I guess you're. I see some quizzical faces here. Are you wondering how you get this to be beta? No, okay. I'll let you verify that. Basically, the point is that the diagonal components of C represent the normal stretch square of the normal stretches in each of the E1, E2, E3 directions. The off diagonal components of C represent the shearing components. Okay. Here is another example that um, that that should help you understand the effect of deformation. What I'm doing now is taking a unit square. I'm going to give it a map which I'm calling simple extension. Simple extension in the Z1 direction. So all I'm doing is take whatever was in Z1 and displace each and every point with beta times Z1. So the net map becomes 1 plus beta times Z1. Z2 remains same, Z3 remains same, which I'm not even writing here. So you can imagine that this guy, after deformation, all that it does is, if I pick this out, initially it was this, and all I'm doing is I'm stretching it in the x direction and just moving it to a new coordinate system just so that we can see it clearly. So as I do this deformation, take very careful notice to each and every tangent vector that I've drawn. Right? This was the original direction. This was the original configuration. Look at each one of these tangent vectors that I have. Tell me, are there any tangent vectors which do not change direction, and which are the tangent vectors that do change direction? Okay. So when I do that, are there tangent vectors that don't change direction? Which ones? Any tangent vector that is along E1 and E2 does not change direction. Any other tangent vector does change direction, right? Even in this simple extension example, there are tangent vectors that will change direction. The whole point here is, if I measure the shear between two tangent vectors, even for a simple extension example, you might be tempted to think there is no shear. There is shear. Why? Because look at any other pair of tangent vectors, right? Except for E1 and E2, there is no shear between E1 and E2. But every other pair of tangent vectors has shearing between them. Why? Because the angle initially and the angle finally is different. Correct? So even in an example like a simple extension, there is shear between lots and lots of different infinitely many tangent vectors. It's only these two that do not have shear, which is basically what this fact is not captured by the off diagonal components of C in this case, because um, because the C is with respect to the G1, G2, and the E1, E2 coordinate directions. There is clearly no shear in the G1, G2, or the E1, E2 coordinate directions, but every other pair does have shearing. Okay, all right. Let's take a look, sort of this idea of whether tangent vectors change direction or not, kind of normally, naturally leads to this idea of principal stretches, principal strains, which, as you might imagine from our chapter 1 discussion on tensors, these are the principal eigenvalues and eigenvectors of the deformation tensors. You remember when we were talking about principal directions and principal values of tensors, we placed a certain restriction on the types of tensors that we were looking at. What did we say about that? Symmetric tensors only, right? Because if a tensor is unsymmetric, its components, of course, will not be symmetric. We won't get a symmetric matrix as its components. The eigenvalues of an unsymmetric matrix can potentially be complex. For a real problem, we don't want to deal with complex numbers. So that's why we said that we'll restrict ourselves to symmetric tensors. Now let me ask you this, is F symmetric? F tensor is not necessarily symmetric. Is C symmetric? Yes. So C tensor is indeed symmetric because it rules out, or it kind of factors out, the rigid body rotation, and hopefully we'll get to that today. Maybe not. But C, we can calculate the principal values and principal directions of C tensor to get some idea of what might be the directions of principal stretches and strains. So we'll do the same exercise here. What I'm showing you here is that this was the simple stretch example. We said that in the simple stretch example, the vertical and the horizontal do not change directions. Similarly, for the simple shear, this was simple extension, this is simple shear, there are two particular directions which do not change direction. They are at this angle. They are actually the minor and major axes of the resulting ellipsoid. How do we find these directions? Let's see if we can set up something like that. Now, another thing to note here is that in the directions that don't change, right? In the directions that we have major and minor axes of this ellipsoid, in these directions, the tensor reaches an extremal value, a minimum or a maximum value. Okay, so if we can write the stretch, or if we can find the directions in which the stretch is minimum or maximum, those would be those directions. So stretch in any direction is written as lambda square is equal to n dot with Cn. If I were to ask you to try to maximize this function, how would you do this? If I give, okay, first of all, is this a scalar or is it a vector or a tensor? Scalar, right? Tensor acting on vector is vector, dot with vector is another vector. Indeed, it's a scalar, which is the square of the stretch in the n direction at a point. If I ask you to maximize a scalar function, how would you do that? Take the derivative, set it equal to 0, right? If you do that, in this particular case, what will happen is one of the possible solutions is that just take bigger and bigger n vectors. There's no maximum as such. So to get a well-defined maximization problem, what we have to do is to subject the maximization to a constraint. That constraint is that n has to be a unit vector. That's what we are saying here. Otherwise, there is no solution to maximize this. You just keep getting bigger and bigger n vectors. There's no end to that maximization. So unless we have this constraint that n has to be a unit vector, once we say that this is a constraint, then we can maximize it. And a good way to do that is through a process of constrained maximization or constrained minimization. Anybody done optimization? Right? Um, if I uh, give you a function f, and if I give you a constraint that, let's say, maybe it's kind of tricky to draw that, but maybe I'll just give you some crude idea about what I'm talking about. So let's say I have this function f of x, okay? Um, and normally we would have a third axis for lambda, but let's not get into that. I'm also saying that there is some point x0 where which I will involve in my constraint. So I'm going to say that find the minimum of f of x subject to the constraint that um, x has to be less than x equal x0. That's an example of a constrained minimization problem, right? The true minimum of the function is right here. True minimum is right here. But this does not satisfy my constraint x should be less than x0. So the solution that I should get is here. That's the solution I want to pick. So one way to do that is to, and actually this is an inequality constraint. What we are talking about is an equality constraint, as in minimize or maximize this, which is lambda square, minus some parameter mu and times the constraint. N dot n equal to 1 if this is the constraint, and if we try to minimize this function, then we will get a possible solution to this. So let's see what we get. Partial of this Lagrangian function, this L stands for Lagrangian, so this partial of this Lagrangian function with respect to n, what would that be? Lambda square n is nothing but n dot with Cn. So what we get here is C acting on n, and derivative of this with respect to n is minus mu n. Derivative of 1 is of course 0. So that gives me Cn minus mu n should be equal to 0. Similarly, derivative with respect to the second variable, derivative of Lagrangian with respect to mu, this one does not depend upon mu. This we just get the constraint back, which is n dot n. I'll just write it in the same form, minus 1 equal to 0. So does the first of these equations look familiar? Cn is equal to mu n. Does that look familiar? This is the eigenvalue problem. Remember back in chapter 1 when we were dealing with tensors, components changes, tensor invariance, and principal invariance. We said for any tensor, Tn is equal to lambda n is the eigenvalue problem that we wanted to solve. Here, all we are saying is solve Cn is equal to mu n being the lambda, being the eigenvalue. So this is indeed the eigenvalue problem for finding the eigenvalues and eigenvalues mu and eigenvectors n of the tensor C. And since C is symmetric, this is a well-posed problem. Further, we have the constraint that whatever n you find, we have to normalize it to be an to be a unit vector, which we have already been doing. So there's no change there. But a useful way to interpret eigenvalues of C is as follows. You remember we said square of the stretch in any direction is ni. Again, I'm missing a dot. Ni dot with C acting on n, which if you look at this part, Ci times Ni would be equal to mu times Ni dot with Ni, that part is 1. So we get mu is equal to square of lambda, which means lambda is equal to square root of mu. So the eigenvalues mu of C, take the square root of that, that would be the stretch in one of the eigendirections. Okay. Going back to, for example, this, the simple stretch example, we can practically eyeball here that these two directions are the eigenvalues, eigendirections. The corresponding eigenvalues in the E2 direction would be 1, and maybe map is on the previous page. It is 1 plus beta Z2. What would be the eigenvalue in this direction? 1 plus beta square, right? 1 plus beta whole square. Is that right? 1 plus beta whole square would be the square of the stretch, which indeed it is, and that is basically what this is saying. Similarly, for the simple shear example, if you solve this eigenvalue problem, you will see that what you get are two eigenvectors in these I believe 45-degree angle, and in one direction you get shorter, in the other direction you get longer. And let me ask you this now. These two angles, or sorry, this direction and this direction, let's call this N1 and N2. Do these directions change when we go to the deformed shape? So keep in mind that the actual deformation is happening through F. So if you look at this direction, it does, the N1 direction will rotate a little bit. Similarly, the N2 direction will be rotating the exact same amount towards the right. But the relative angle between N1 and N2, that is initially 90 degrees, it will stay 90 degrees. So there will be rotation of these eigenvectors because the relationship between the undeformed tangent vectors to the deformed tangent vectors is through F. It's not through C. C rules out the rigid body motion. Okay, and we'll see another interpretation of F probably next time that will help us understand that. Very quickly, since I've done eigenvectors of C, you can verify some of these relationships. Shear between two eigenvectors is pi over 2 minus cosine inverse of, what would this be? Ni dot C and J. C and J would be mu J Nj. Do you agree? So what we would get would be mu J Ni dot Nj divided by lambda Ni and lambda Nj. Denominator remains the same. What is Ni dot Nj? If I have two eigenvectors, n1 and n2, the dot product between those eigenvectors is, it is 1 if we have I equal to j. If I is not equal to j, dot product is 0, which is what? Lambda ij, sorry, delta ij, Kronecker delta ij, right? So, which is basically going to be 0, and cosine inverse of 0 would be pi over 2. So what we get there is that the change in angle would be 0, which means that if you calculate all the three eigenvectors, the initial angle between them, of course, was 90 degrees. Even after deformation, that angle will remain 90 degrees, which is what I showed you here as well with in this simple shear example. These two eigenvectors initially had 90 degrees, finally also were 90 degrees. All right. let's stop here and we'll continue off of this after quiz 2. On Monday, we will have a review session in class, and today as well, from 3:30 onwards, we'll do a review of some of the calculus topics and the kinematics topics that are on the quiz. Okay, so I'll see you on 3:30 or on Monday.